I'm Hakyeong from KAIST Korea. This is a collaborative work with Andreas Meuleman, Hyeonjoong Jang, James Tompkin, and Minhage Kim. We will present a neural scene reconstruction method called OmniSDF using omnidirectional sign distance functions and adaptive Binoctrees. Since NERD-based neural rendering was introduced, recent work have reconstructed the mesh from an image set by training neural implicit functions with volume rendering. Their work have in common that inputs are all captured by perspective cameras. In this work, we reconstruct the geometry of large outdoor scenes given egocentric videos captured by a circular sweep of a 360-degree camera on a stick. The motivation of our work is to reconstruct geometry from a dataset that can be captured with simple and compact setup. Unlike a perspective camera with a limited field of view, this setup drastically reduces the capture time and the calibration costs. However, given equivalent image resolutions, a 360-degree image causes sparsity in ray crossings, and a narrow baselines of the camera trajectory involves high disparity estimation errors. This ray sparsity deprecates the quality of the reconstructed mesh when using existing neural surface reconstruction algorithms. Therefore, we propose a method to mitigate this challenge. First, we extract a 3D point cloud with a pre-trained spherical stereo estimation network. Then, we formulate a normalized spherical space by setting the near bound sphere encapsulating all cameras and the far bound sphere holding the region of interest. Still, we must handle the ray sparsity and the extensive sampling range to train neural implicit function. We thus create a voxel grid that memory efficiently subdivides spherical space and bounds the subspace where surfaces might exist. This allows us to densely sample the region with a higher probability of object existence, consequently enabling us to compute the expected surface distribution with higher accuracy. To do so, we use a spherical binoctree structure which subdivides the spherical volume in radial and angular directions, so that a spherical voxel called voxel is bounded by spherical coordinates. It efficiently subdivides the spherical space and better copes with a large outer scene with a large variances in disparity. Given initial steady scene points, we iteratively subdivide the space till the size of the bounding voxel reaches the threshold solid angle. Given initially subdivided binoctree, we devise stepwise spatial sampling strategies using this grid structure. To implement voxel-guided sampling, we design a voxel ray intersection modules beforehand. We approximate the voxel as a cuboid and compute the intersection of the ray with every 12 triangles that constitutes a cuboid. If a ray has a pair of front-facing and back-facing intersections, we determine that it intersects with the corresponding voxel. Then we retrieve all intersecting voxels with a breadth-first search and do the sparse sampling at every intersecting segments. Coarse voxels are selected by collecting the grandparents of leaf nodes of the initially subdivided binoctrees. Then, we prune if the points contained in the voxels are less than the threshold. As a result, we can sample ray sectors that intersect with surfaces. However, we need to sample more densely near the surface for sharper reconstructions, so we devise adaptive fine sampling. Our idea is to subdivide the coarse voxel trial during the training. At every 10,000 iterations, we test surface existence, mark as fine voxel, and subdivide the marked voxel for future fine voxel designation. Based on the definition of the sign distance function, we can presume that a surface plane passes through the voxel by comparing the magnitude of the trained SDF with the radius r of the voxel's circumscribed sphere. For example, the marked fine voxels after 200K of training for a sponge scene were distributed as follows. We can retrieve the voxel near the surfaces in finer resolutions and sample denser near the surfaces. We show the strengths of our method over classical methods and the neural methods qualitatively with the rendered mesh. This video shows that our method reconstructs the geometry more accurately and with high fidelity details than other neural methods. Compared to the mesh that is reconstructed with the classical methods, our method reconstructs as accurately as those with smoother and more expressive surfaces. In conclusion, we reconstructed a mesh of a large scene captured with 360-degree videos. We devised voxel ray intersections and surface existence test algorithms adjusted for the irregular shape of the voxels, and suggest a stepwise sampling techniques that is guided by coarse voxel and adaptive fine voxels. As a result, we could subdivide the Binoctrees adaptively online to optimize both Binoctree structures and neural implicit functions for more accurate and delicate mesh reconstructions. Thank you for watching.